Hi everyone. So as Sarah said, I'm Adriana, and this summer I was at Purdue working with Dr. Welp and my two co-advisors, Dr. John Sloan and Dr. Tim Philly. And we are also part of the CINet, or the Critical Interfaces Network research group that Justin and Sydney were also a part of. And for context, CINet is really focused on looking at intensely managed landscapes, and especially how sediments, nutrients, water, and carbon are transported and transformed through those landscapes. And so my project in particular looked at water flow pathways in an artificially drained agricultural landscape, and we looked at that using water-stable isotopes and electrical conductivity tracers. And the main focus of this, and as it relates to CINet, is that the agricultural soils can function as a really complex biogeochemical reactor that determines the nutrient concentrations in the water samples that we looked at. So when we talk about artificially drained, in this project we are looking at tile drains. And you've probably all seen the outlets, especially in the Midwest. They're pretty common, and you can see large volumes of waters flowing out of them. And if you look at the map, the Midwest by far has the largest concentration of tile drained land, and the purpose is to increase soil aeration and quality. They transport water really quickly and directly through soil. It cuts through natural flow pathways and makes it more efficient, and also prevents flooding. But while doing this, they increase nutrient export, and especially nitrogen and phosphorus. So as Faith discussed before lunch, this excess nitrogen and phosphorus can cause eutrophication and eventually contribute to dead zones. So tile drained lands have higher nitrate concentrations, and when these excess nitrates enter the waterways, cyanobacteria growth increases and algae blooms, and as they decompose and block sunlight, overall the region becomes oxygen depleted and cannot support an aquatic ecosystem. So before it gets to this tile drain, the water can flow through the soil in different pathways. Two major categories are macropore flow or non-macropore flow, which we call matrix or micropore flow. So on the diagram, macropore flow, as you can see, it's large cracks in the soils, large crevices that water flows through quickly. It doesn't have time to linger and interact with the soil aggregates. There's less biogeochemical reactions taking place. In contrast, matrix water is held in these soil micropores, those small spaces in between the larger soil aggregates. It's a slower pathway, water seeps through it, and it has a lot of time to interact with elements such as nitrates and other aspects of the soil. So in general, the nitrate forms and interactions differ with these water flow pathways. So with that background, our fundamental question really focused on, can we predict nitrate variability before, during, and after a precipitation event? And we looked at that through the lens of matrix water, that micropore matrix water that's held in the soil for longer amounts of time. Does the fraction of that water flowing through tile drains in each event explain nitrate variability? And the chemical tracers we used were electrical conductivity and stable isotopes. The site was the Allerton Trust Farm, and these samples were collected in 2016 and 2017. And in the past, they had been analyzed for water-stable isotopes, nitrate concentrations, anion and cation concentrations. And in the site, there was continuous measurements of tile drain discharge and electrical conductivity. So if you can look on the diagram, there's the structure for water control. That is where the water samples were auto-sampled during these years, and was where we got those samples, or how we got the data that we later analyzed using MATLAB. So in the next couple slides, we're going to be looking at two events that we chose. In total, in this project, we looked at 4 events, 3 from 2017, 1 from 2016. Event 4 is from 2016, and event 6 is from 2017. And when comparing these events, key measurements are soil conditions prior to the precipitation event, nitrate concentrations measured in the water samples, from the tile drain discharge, particularly oxygen 18, which is a heavy isotope of oxygen that's commonly used to identify water sources. And then we also looked at electrical conductivity, which is the amount of electrical current the sample can conduct. So the first question we asked when looking at data was, does peak nitrate occur at peak discharge? Does the moment where we had the most event water or the new water added in this precipitation event, does that line up with when nitrate concentration was the highest? And for event 4, the answer is no. There was a delayed nitrate peak. Nitrate peaked around August 18th, which was 2 days after discharge had peaked. You can also see highlighted here in that bar the relationship between electrical conductivity and tile drain discharge. As discharge reached its peak and increased, you could see electrical conductivity decreased, which was one of those key chemical tracers that we looked at to determine the fraction of matrix water versus macropore water. It's also worth noting that the soil conditions prior to this event were most likely a dry summer soil. This event was in late August of 2016, and so the soil's drier, there's more likely large cracks, and the water can flow through those quickly and not interacting with the soil matrix as much. So there is evidence for macropore flow here. Like we said, there is a drier soil condition, more cracks in the soil, less time to interact with the matrix, which you can see on the left-hand graph here. There is a decrease in electrical conductivity where the event water bypasses the soil matrix. The nitrate concentrations are still staying relatively low. And then there's that pulse of matrix water, the water that was held in the soil micropores and has the higher nitrate concentration, which is the spike. And then after that, there's the discharge slows, the water is moving slower, and there's a general return to pre-event conditions. On the right is looking at the oxygen 18 isotopes, and there is the initial spike in nitrates early on in the event, and then there is the oxygen 18 shift when new water is added into the system. That's a pretty significant shift in concentrations based off what we looked at, and we can just conclude that new water was added to the system. Something is there now that wasn't there before. And then again, there is that delayed peak. There's a 2-day difference between nitrate concentrations being at their highest and the most volume of discharge, which is all, again, evidence for macropore flow, as you can see in the far diagram with those large cracks moving quickly towards the tile drain. In contrast, Event 6 was very different. Event 6 was a small precipitation event in late March of 2017. In contrast to Event 4, Event 6 does not have the delayed nitrogen and discharge peak. The peak nitrate occurs simultaneously with discharge, and we also assume these soil conditions to be wet spring soil. It's more saturated, there's fewer cracks and larger spaces in the soil. And again, you can see that relationship between electrical conductivity and discharge highlighted in the two graphs on the top right corner and bottom right corner. So Event 6 is evidence for matrix flow, which is the micropore water again. And the graphs are a lot less dramatic here than you can see in Event 4. There's a return to pre-event conditions that you can see later in the graph. The lighter colors are later in the event. But in general, the nitrate concentration doesn't have the same significant spike, the same pulse that we saw in Event 4. There is some flushing that goes on in this event, which does explain the increase in general. As the water moves through, the soil matrix is flushed through the system. So there is a spike, but not the same matrix water pulse as before. But in this event, you can see that the water is seeping slowly through micropores, and it's mobilizing nitrates as it moves. Another interesting result that we found was looking at nitrogen dynamics in Event 4. The 2016 events had been previously analyzed for nitrogen-15 isotopes. And so when we plotted this, it showed evidence of denitrification occurring. There's really high concentrations of nitrate, nitrogen-15 concentrations, as well as O18. And so that's most likely through fertilizers, and that denitrified nitrogen pushed through early in the event, or occurred early in the event in anoxic conditions. So after these results, we were able to come up with some conclusions, and we were able to distinguish between macropore flow and soil matrix water. So the macropore flow was characterized by lower electrical conductivity and nitrogen concentration. It was more likely in that dry summer soil when there was larger cracks for the water to flow through quickly, which also explains the delayed nitrate and discharge peak. And that was seen in the first event we looked at, event 4. Then we looked at matrix water flow, which is event 6. And overall, matrix water held in the micropores had higher electrical conductivity and nitrate concentrations. It was more likely in that wet spring soil when conditions were conducive to that slow seeping movement of water. And then again, it had that simultaneous maximum discharge and nitrate peak. So looking ahead, we hope to continue this project and look for evidence of denitrification early or at all in the other events. We currently have nitrogen-15 isotopic analysis running on the other 3 events, and so that is a question hopefully we'll be able to investigate soon. And then we also want to know if there's an influence of groundwater or a high water table in any of these events. We did collect some groundwater samples from the site during this internship, and so we can analyze those for some of the similar tracers we've been looking at before and other stable isotopes and see if that interfered in any of the concentrations. And then another possibility is dissolved organic carbon concentrations on all the events. So I'd like to thank NGRREC for this internship, as well as the Purdue Stable Isotope Facility and Dr. Welp for working with me. And if there's any questions, I can take this now.
That was really interesting. So how do you, well not you, but anybody, how do you distinguish between a macropore and a micropore, or is it just sort of a, after the fact estimation of what's going on?
The micropores are like in the soil, and the water is held in there between the larger aggregates. And then the macropore are just really larger spaces filled with air rather than water. And the water can flow through the macropores, but the water is held in the micropores.
So do you know, like, would you say that this soil has a lot of macropores, not because you're looking at the soil, but you're just looking at how fast the water runs through it? You know what I mean? So I guess, like, how do you distinguish, like, a macropore soil and a micropore soil?
All soils have both. So I guess you could look at the speed of water moving through it. If it is moving through the macropores, it will be faster because it's not being held in the soil in the micropores and interacting with the other soil aggregates. So speed is something you could look at.
Well, I was going to follow up on Jason's. Could it be, what's the background of these sites? I mean, could the existence of macropores or micropores be related to the way the soil was managed before or tilled?
It's all been used for agricultural reasons. We didn't investigate that question in depth, but from what we found in like land management practices, it is possible that soil had been compressed a lot more and compacted, which may lend itself to more micropores versus macropores, but we didn't investigate that during this project.
But what were the sites, and I'm sorry if I missed that, what were they used for, these? You say agriculture uses, but like were they tilled?
I believe they were
growing crops?
Yes, for crops. I'm not sure if they were tilled. I'm not sure of the exact land management process, but it was crops.
Okay. Yeah, typically you would see the macropores in the no-till and in the micro. You wouldn't see those macropores in the tilled soil because they've been destroyed. That was good work. Okay, that's one more. The N15. Did they put out N15 fertilizer at some point?
We do think it was from fertilizer. I don't know especially about N15, but it's the most likely source especially because the nitrate and N15 concentrations against the O18 were so high. It's the most likely source was some sort of fertilizer.
Dr. Welp just chimed in and said the cracks can change with land management, but also due to environmental wet or dry conditions.
So this topic is very interesting to me. So what were the soil textures? Were they like? Do you know?
I don't know exactly what the soil textures were. I'm assuming like a loam, probably more of a silt loam from the region, but I'm not sure on the exact textures.
Yeah, Dr. Welp would probably know.
Yeah.
More clay.
I may be wrong on that.
Yeah, you would see those cracks kind of form in the soil with more clay.
She just responded. She said the cracks can change. Pretty high clay. That's it. Okay.
Thank you, Dr. Welp.
I always thought that tile drainage was for just draining and not for oxygenating the soil. That's new to me. Is that, can you elaborate on that? Is that done on purpose, or is it, I just think that they just put tile in just to get rid of the water, but maybe because it's waterlogged, doesn't have oxygen in it. Okay.
Yeah, I think that's probably the relationship is exporting more water out of the fields would allow for better aeration, better management, and overall healthier soil.
Okay, all right, okay, yeah, I think I answered my own question.
Thank you.